Yeah, I think we're recording. Okay. Cool. All right. Well, a very warm welcome from the UK in Bristol. Thanks for joining our talk on our work training neural networks in low-dimensional random basis. There's going to be our poster session tomorrow, but this talk is going to be an overview about the work and also going to give a bit more background information, that's sort of the story behind the work, really. And my name is Frithjof, and with me presenting today is Zach, who is going to kick off the talk by just giving a brief introduction of Graphcore and Graphcore research.
Yeah, hello. We're Graphcore. We're a company from Bristol in the UK who have designed hardware chips from the ground up for machine learning. We already have multiple chips in production. The work here was done on our first chip, which has been out since about mid-2018. We'll talk a bit about that at the end, but really it's just to say that as Graphcore research, it's really cool to be able to work with the latest technology, and that's what we did this work on. So yeah, at Graphcore Research, we do fundamental machine learning research, and there's actually another expo talk on Wednesday, if you're interested. We look at problems, and our particular sort of leaning as a research group is to try and get the new perspective that's caused by having a slightly different set of hardware than what most people are using. And as a team, we're trying to understand the progress, direction that machine learning research is taking, as well as influencing it and steering it, and seeing what can really bring about the best algorithmic changes with our new hardware. But now I'm going to pass over to Frithjof to talk a bit more about this particular work.
Yes, so this is briefly the agenda that we're going to talk about. Two main points. One is obviously presenting the work that we've done and that we're going to present at this conference. But then, as I mentioned in the beginning, I also want to talk a bit about the background and in particular the role of hardware in this work. So let's first talk about the motivation of this work. As you all probably know, there has been this massive increase in number of parameters in state-of-the-art architectures, particularly in natural language processing. There has been this staggering increase of model size and accuracy. I think this conference has lots of work in this area that demonstrates this increase. And this is a big opportunity, but also poses new challenges because now we have to find ways to efficiently train these very large models that are today very expensive to train. And from the literature, there's some evidence that it might actually be possible to optimize these networks by only considering a smaller subset of the available weights so that we don't have to train the fully overparameterized model at the same time. So the motivation for this work, or the question that we asked ourselves, was really, can we maybe train these models more efficiently by considering only a smaller fraction of the available descent directions? And one of the starting points of our work was this ICLR paper measuring the intrinsic dimensionality of neural networks, which had a very simple approach of sort of restricting and downsizing the available optimization space by projecting it into a random subspace. And that worked surprisingly well, I would say, but also had lots of shortcomings in terms of accuracy that you could achieve. And so starting from this, we set out to basically improve on this work, and with the overall view to ultimately improve sort of efficient training, which would allow us to scale to much larger models. So here's a picture or illustration of our approach. You can see the loss surface in a bluish color here, and the normal SGD gradient computed is denoted in orange here. And what we would do now is basically sample a random subspace that is illustrated in green here. In this case, just two random directions sampled from a standard normal distribution. And so what we do is we compute the gradient with respect to these 2 dimensions and then descend. And as you can see, the gradient in the subspace might not be the same gradient as in the full dimensional space, but so we hope, the hope is that this will still lead to very good optimization outcomes. And that's really the question that we were asking in this work. And I'm just going to highlight 2 findings of this work. The first one being that redrawing the subspace helps and makes the outcome of the optimization much better. So here we see 3 different algorithms compared on a ResNet 8 CIFAR10 datasets. And it's for very low dimensional random subspace. So it's only 250 dimensions, while the overall network has close to 100,000 dimensions. And so the first thing is a black box optimizer at the very bottom, which is a derivative-free optimization scheme. So it doesn't actually compute the gradient, it just approximates it through forward passes. And then the second approach is sort of prior work, where you choose a fixed random subspace at initialization and you don't evolve it, you just descend on that particular hyperplane. And as you can see, it reaches a certain accuracy, but it doesn't converge to the accuracy we wanted to converge to, which is SGD level. And then we have at the top our approach, which resamples the projection at every step. So this gives the optimizer much more freedom to explore. And as a result, you see much better convergence. And then the second finding I like to highlight here is sort of why we're interested in this, which is that these optimization schemes might be more efficient. And the reason being that if you calculate a low dimensional gradient, it has fewer elements. So if you want to distribute it to many workers, your gradient that you need to communicate is much smaller, and therefore it's more efficient. And so one thing that was important to ask was, well, if we distribute our workload in this way, so where every worker gets an independent set of projections and then you exchange these lower dimensional gradients between them, how does it affect our convergence and accuracy that we achieve? And you can see here that when you scale from 1 to 16 workers, the accuracy that you achieve actually doesn't vary much. So it's a very easy way of distributing this method. And on the right, you see that you gain a lot of sort of efficient compute, because you can now linearly scale your wall clock time down and train much faster. So this is the first part, basically introducing our work. And now I want to talk a bit more about the background and the role of hardware in this work, which is something that you might not immediately sort of spot when you see this work, but is definitely played a big part in it. So as I just introduced the method, basically one of the key things in this method is that we redraw the random projection at every step during optimization. And this is obviously a very simple conceptual change, but in practice, it actually turns out to be much more difficult to realize in the actual experiments. Because the problem is, if you start changing this fixed random projection, it becomes quite challenging on conventional hardware to properly accelerate training, because as you can imagine, the sort of generated projection now need to be fetched from memory and brought to where the compute and the matmulls happen and so on to actually evaluate the network, which is computationally demanding. And that might actually be also one of the reasons why in prior work this fairly simple change wasn't considered, because in practice it turns out to be difficult. And we were fortunate enough to actually have access to the first generation of our intelligence processing unit called IPU, and it has been designed from ground up, as Zach mentioned, so it has this very unique architecture. It actually consists from out of 1,200 tiles, and each of these tiles, as we call them, contains its sort of independent compute unit that has memory as well as compute and as random number generation sitting right next to each other. So as you can imagine, if we are now actually computing a forward pass with this random projection, what we can do is we can basically generate the random numbers that are necessary for this projection right where the weight and the matmul happens, because all this is locally available to the tile. And so the IPU and this tile architecture here gives us a very interesting advantage. And in practice, what this means is that we can store much larger projections. The reason being that we actually never have to keep the full projection in memory. What we do is we only generate it on the fly during the forward pass and then regenerate it on the fly during the backward pass. So we can fit much larger models and actually execute that fairly efficiently, because we substitute this local compute for fairly expensive communication. And so, and just to give it a bit better idea of what that means for our experiments, so if we run this algorithm on conventional hardware, it becomes quite prohibitively expensive. So here we have a CIFAR-10 convolutional neural network and quite a large projection. So it's 10,000 dimension, which would be, yeah, it's quite tricky to fit on conventional hardware. And I must say that this is just a very normal TensorFlow implementation. We actually released our source code, so you can go and have a look. But when we are running this TensorFlow implementation on the IPU, we see the advantage of this architecture that we can actually train much faster. So in this case, we can just finish this experiment in over an hour. And I think it's not so much about the sort of that we have to wait around for 13 hours to see our result. I think it actually enables us to ask questions that we wouldn't ask ourselves with other hardware, because it would just take too long to evaluate ideas. So this quick turnaround time with new ideas is really making a difference for our work here. And to summarize, I think, so our work provides a bit more evidence that neural networks can be optimized by exploring only a small fraction of directions in the native weight space. I think there's lots of work to follow and lots of exciting work already going on in this direction, how we can train neural networks that way. I also think there's still lots of scope for improvement. So in future work, we would be excited to evolve the sampling distribution that in this work has only been a fixed standard normal distribution. And so we would be, yeah, very interested in any more ideas and push this idea further, because as we mentioned earlier, we see this as one possible idea to be able to scale to much larger models in future. And that's it. Thank you very much for attending this talk. If you have any more questions, feel free to find us at the NeurIPS virtual booth or in our poster session tomorrow, as we mentioned in the beginning, or just reach out to us at any point during this conference. I hope you all enjoy the conference and have a good day or night or wherever you are. Thank you.